Download this code from codegive.com, link in the description below. OK, let's dive deep into the issue of non-volatile variable storage is about full, often represented by an error message including a hexadecimal address like 00c08290 in the context of embedded systems programming, particularly when working with microcontrollers. This is a common problem, especially as projects grow in complexity. I'll cover the causes, consequences, diagnosis, and, most importantly, solutions with code examples. Understanding the problem. When you see an error message that states non-volatile variable storage is about full, address, 00c08290, or similar, it indicates that the region of memory designated for storing variables that need to persist even when the power is turned off, or the system resets, is nearing or has exceeded its capacity. Non-volatile memory, NVM. This type of memory retains its contents even when power is removed. Common types of NVM used in microcontrollers include flash memory, widely used for program code and often for configuration data and limited data logging. It's typically the largest form of NVM in a microcontroller. EEPROM, electrically erasable programmable read-only memory, smaller than flash memory. EEPROM is designed for more frequent writing and erasing, but it also has a limited lifespan, number of write cycles. It's often used for storing settings, calibration data, and small amounts of data that need to be preserved. Some microcontrollers emulate EEPROM in flash. FRAM, ferroelectric RAM, less common, but provides much faster write speeds and higher endurance compared to EEPROM or flash. More expensive. Volatile memory, RAM. This type of memory loses its contents when power is removed. It's used for temporary data storage during program execution. Variables declared within functions or local variables within your code are usually stored in RAM. Why it's important. Non-volatile storage is critical for settings persistence, saving user preferences, configurations, and calibration values so that they don't have to be re-entered every time the device is powered on. Data logging, storing sensor readings, event logs, or other data that needs to be preserved across power cycles. State management, remembering the state of the application or device, example last known operating mode, a partially completed process, after a reset or power failure. Firmware updates, storing the updated firmware image before it's applied to the main program memory. The hexadecimal address, example 00c08290. The hexadecimal address in the error message is a crucial clue. It indicates the specific location in memory where the overflow or near overflow is occurring. It will be within the memory range assigned to the NVM, likely flash or EEPROM. You'll need to consult the data sheet or memory map of your specific microcontroller to determine which type of memory this address falls within and therefore what is filling up. The specific address will vary depending on the microcontroller and the compiler/linker configuration. Causes of the problem. 1. Excessive use of EEPROM/flash for variables. This is the most common cause. You might be storing too many variables, large data structures, or frequently writing to NVM. 2. Inefficient data storage. Storing data in a way that consumes more space than necessary, example using strings instead of numerical codes. 3. Unintentional or uncontrolled writes. Writing to NVM too often or in loops without proper safeguards. NVM has a limited write/erase cycle count. 4. Data corruption. If data gets corrupted in NVM, it can appear as if the memory is full, even if it's not entirely used. 5. Incorrect memory map / configuration *. An improperly configured linker or memory map can cause the compiler to place variables in the wrong memory region, leading to an overflow. 6. Compiler bugs / issues *. Rare, but sometimes the compiler might generate code that uses NVM inefficiently or has bugs that lead to memory errors. 7. Using string literals directly in EEPROM.put, storing string literals directly with EEPROM.put, or similar functions can be problematic. String literals are typically stored in flash memory, and copying them to EEPROM can be inefficient and lead to memory exhaustion. See example below. 8. Using third-party libraries *. Some libraries, particularly those designed for configuration or logging, may use NVM. Consequences. Data loss *. If you write beyond the available NVM space, you'll likely overwrite existing data, leading to loss of settings, calibration values, or logged data. System instability *. Writing to invalid memory locations can cause the microcontroller to crash, reset unexpectedly, or behave erratically. Reduced NVM lifespan *. Excessive writes to EEPROM or flash memory will shorten its lifespan, as these memories have a limited number of write/erase cycles. Unexpected behavior *. In some cases, writing beyond the available space can overwrite parts of the program, leading to extremely unpredictable behavior. Diagnosis and debugging. 1. Code review *. Carefully review your code to identify all variables stored in NVM, EEPROM or flash. Look for functions like EEPROM.put, EEPROM.update, or similar functions that write to NVM. Also, look for any custom implementations you might have created for NVM storage. 2. Memory mapping and linker files *. Consult the microcontroller's datasheet and the linker script used for your project. Understand how the memory is divided and which regions are allocated for EEPROM/flash and RAM. Make sure the linker is configured correctly. 3. Variable size audit *. Check the sizes of all variables that are being stored in NVM. Use the size of operator in C/C++ to determine the memory footprint of each variable. Large data structures, such as arrays, structs, or classes, can consume significant amounts of NVM. 4. Write frequency analysis *. Determine how often your code writes to NVM. Excessive writes, especially in loops or interrupt handlers, can quickly exhaust the available space and reduce the lifespan of the NVM. Use debugging tools, breakpoints, serial output, to monitor the frequency of writes. 5. Address verification *. Use a debugger, if available, to inspect the contents of the memory location reported in the error message, example 00c08290. See if you can determine what kind of data is being stored there and where it's coming from in your code. If you have a memory dump tool, that can be helpful as well. 6. Compiler warnings *. Pay close attention to any compiler warnings related to memory usage or data sizes. The compiler might be able to detect potential overflow situations. 7. Disabling features *. As a test, try commenting out sections of your code that involve NVM storage. This can help you isolate the part of the code that's causing the problem. Solutions. Here's a breakdown of solutions, ordered from the most common and practical to the more advanced. 1. Reduce the number of variables stored in NVM. Move variables to RAM. The simplest approach is often to move variables that don't absolutely need to be persisted to RAM. If a variable's value only needs to be maintained while the device is powered on, there's no need to store it in NVM. Reevaluate data requirements. Can you eliminate any variables altogether? Are you storing information that is unnecessary or redundant? Asterisk consolidate variables. Asterisk if you have multiple variables that represent related pieces of information, consider combining them into a single structure, struct, or class. This can reduce overhead and improve memory usage. 2. Optimize data storage. Asterisk use smaller data types. Asterisk use the smallest data type that can accurately represent the data you're storing. For example, if you're storing a value that ranges from 0 to 100, using a byte, 8 bits, instead of an int, 16 or 32 bits, depending on the architecture, will save space. Asterisk use numerical codes instead of strings. Asterisk avoid storing strings directly in NVMe if possible. Instead, assign numerical codes to represent different states or values and store the codes. This can significantly reduce the memory footprint. Asterisk bit fields. Asterisk if you have multiple Boolean flags or small integer values that can be packed together, use bit fields within a struct or class. Bit fields allow you to store multiple values within a single byte or word. 3. Reduce write frequency. Asterisk batch writes. Asterisk instead of writing individual variables to NVMe every time they change, accumulate the changes in RAM and write them to NVMe in a single batch. This reduces the number of write cycles and improves efficiency. Asterisk debouncing. Asterisk if you're writing to NVMe in response to user input or sensor readings, implement debouncing techniques to prevent multiple writes due to noise or fluctuations. Debouncing can involve adding a delay or filtering the input signal. Asterisk only write on significant changes. Asterisk only write to NVMe if the value has changed significantly. For example, if you are logging a temperature, you might only write to NVMe if the temperature changes by more than 1 degree. 4. Data compression. Asterisk simple compression. Asterisk for certain types of data, you might be able to use simple compression techniques to reduce the storage space required. For example, if you're storing text, you could use a dictionary-based compression scheme where frequently used words or phrases are replaced with shorter codes. Asterisk libraries. Asterisk there are libraries available for data compression, examples lib, that can be used on microcontrollers, but these can be resource intensive and might not be suitable for all applications. 5. External storage, if possible. Asterisk external EEPROM. Asterisk add an external EEPROM chip connected via I2C or SPI. This gives you much more space for non-volatile storage. The Arduino wire and SPI libraries can be used to communicate with external EEPROM chips. Asterisk SD card. Asterisk use an SD card for larger data storage. This is often used for data logging applications. The Arduino SD library provides functions for reading and writing files on an SD card. 6. EEPROM emulation in Flash, if applicable. Asterisk many microcontrollers that do not have dedicated EEPROM hardware can emulate it in flash memory. The microcontroller manufacturer usually provides a library or API to manage the emulated EEPROM. This allows you to treat a portion of the flash memory as if it were EEPROM. Note that using flash memory as EEPROM will wear it out faster than using true EEPROM. 7. Advanced techniques. Asterisk wear leveling. Asterisk if you are using flash memory as EEPROM, implement wear leveling techniques to distribute writes evenly across the memory. This helps to extend the lifespan of the flash memory. Asterisk error detection and correction. Asterisk implement error detection and correction codes to protect against data corruption in NVMe. Asterisk custom memory management. Asterisk if you have very specific storage requirements, you can create a custom memory management scheme that allocates and deallocates NVMe space as needed. This is a more advanced technique that requires careful planning and implementation. Code example, common mistakes to avoid. Important considerations. Asterisk microcontroller specific information asterisk always refer to the datasheet and technical reference manual for your specific microcontroller. The memory map, EEPROM/flash specifications, and available libraries will vary depending on the device. Asterisk write endurance asterisk understand the write endurance limits of your NVMe, EEPROM or flash. Exceeding these limits can damage the memory and lead to data loss. Asterisk power loss protection asterisk consider implementing power loss protection mechanisms to prevent data corruption during write operations. This might involve using a capacitor to provide backup power or implementing a transaction-based write scheme. Asterisk testing asterisk thoroughly test your code to ensure that it's writing to NVMe correctly and that the data is being preserved as expected. By carefully analyzing your code, optimizing your data storage, and using appropriate techniques for managing NVMe, you can avoid the non-volatile variable storage is about full error and ensure the reliability and longevity of your embedded system. Remember to always consult your microcontroller's documentation for the most accurate and specific information.